All right. Welcome to another deep dive.
Yeah.
Sometimes you just want to get a grip on one of those really important ideas that kind of underpins a lot of stuff.
Yeah,
right?
totally.
Like one of those things where it's like, okay, if I just understood this one thing, then a lot of other things would make more sense.
Yeah.
So that's what we're doing today.
Yeah.
We're diving into random variables.
Random variables.
Now, it might sound kind of math textbooky, but trust me, it's not as bad as it sounds.
Yeah.
And it's like I said, one of those concepts where once you get it, it's like, oh, okay, I see how possibilities are determined and even how we can simulate those unpredictable parts of the world,
Yeah, exactly. And the sources we're looking at are actually YouTube transcripts from Code Curious,
Oh, cool.
focusing on AP computer science principles,
Okay.
specifically topics 3.15.1 and 3.15.2.
Gotcha.
And it's all about random values, and you might be thinking, computer science, that's not really my area.
Right.
But the beauty of this is that these seemingly technical concepts have surprisingly broad applications.
Yeah.
By understanding how randomness works in this context, you gain real insight into the mechanics behind so much of our digital lives, and even how we try to make sense of uncertainty in general.
Okay, so let's get right to the nuts and bolts of how this is represented in these transcripts.
Yeah.
So they use this thing called random. A,
Okay.
B.
Okay.
You'll see it written like that in code. Sometimes it's even like a little block you can drag around.
Yeah, visual block.
Yeah, exactly. And the really crucial thing here, and this comes straight from the sources, is that the range from A to B is inclusive.
Inclusive.
Right, so if you see random 1, 3, the result you get could be a 1, could be a 2, could even be a 3.
Right.
It's not just the numbers hanging out in the middle, the numbers at the ends are definitely in play.
It's a seemingly small detail, but it is absolutely critical.
Yeah.
It defines the entire set of potential outcomes.
Yeah.
If you misinterpret that, it can throw off your understanding of what's even possible in a simulation or a piece of code.
Yeah, absolutely. And I think when you start to think about it, this idea of randomization, it pops up everywhere.
It really does, yeah.
These transcripts mention classic games of chance.
Yeah.
Like rolling dice, picking marbles out of a bag.
Yeah.
Those prize wheels at a carnival.
Yeah,
But it goes way beyond that.
it does, yeah.
Think about video games you might play.
Right?
When an enemy does something unexpected or a bonus item appears in some weird spot,
Yeah.
chances are that's a random variable at work.
Uh-huh.
And even when we're tackling these huge problems weather prediction or trying to model the stock market,
Right.
the idea of introducing randomness to account for the stuff we just can't perfectly predict,
Yeah.
that's a fundamental tool, right?
Yeah, and what's fascinating here is that the sources make a point to emphasize that the kind of randomization we're primarily discussing at the beginning is discrete.
Okay, hold on. Let's unpack that a little bit for the listener.
Sure.
What does discrete mean in this context?
So in this case, discrete simply means that each time you use this random function, you get one distinct separate whole number from the specified range.
Okay.
It's not like a dial that can land on any value along a continuous spectrum.
Yeah.
It's more like picking one specific marble out of a set.
Gotcha. You can't get 2.5, you get 2 or 3.
Exactly.
Okay, so let's dive into some concrete examples from these transcripts just to really make this solid.
Okay.
All right, so first scenario they set up involves 2 random variables.
Okay.
They define answer 1 as getting a random value between 0 and 2.
Okay.
And remember, that's inclusive.
Right.
So it could be 0, 1, or 2.
Uh-huh.
Then they say answer 2 is assigned a random value between 1 and 5,
Okay.
meaning it could be 1, 2, 3, 4, or 5.
Right.
Now, here's a little mental exercise for you out there listening.
Yeah.
If we have a third variable, answer 3, which is simply the sum of answer 1 and answer 2,
Okay.
what do you think the possible range of values for answer 3 would be? Just take a second, think about it. What's the absolute lowest it could be and the absolute highest?
This is a neat little puzzle that really illustrates how the range of individual random variables kind of dictates the range of their combined result.
Okay, ready to see if your intuition matches the math?
Let's hear it.
Okay, so the absolute lowest sum happens if answer 1 rolls a 0 and answer 2 rolls a 1.
Okay.
0 plus 1 equals 1.
Easy peasy.
On the flip side, the absolute highest sum occurs when both hit their maximums. 2 plus 5 equals 7.
Right.
So the possible range for answer 3 is from 1 all the way up to 7.
Uh-huh.
And it includes every whole number in between 1, 2, 3, 4, 5, 6, and 7.
And as the transcript highlights, because the original random values are discrete,
Right.
their sum will also only take on those discrete integer values within that range.
Right. You can't get 3.5.
Exactly.
Okay, let's look at another classic example rolling a standard 6-sided die.
Okay.
But we're going to do it 3 times and add up the results of each individual roll.
Right.
The transcript presents this and then goes on to discuss like different ways someone might think about the possible total
Right.
and why some of those ways are on the right track and others aren't.
Yeah.
And one idea they specifically point to as being correct is that the final sum will be a range of values.
A range. Yeah.
And why is that?
Yeah.
Well, it's because each time you roll the die, the outcome is independent and random.
All right.
You could get anything from a 1 to a 6 on each roll.
It's true if we connect this back to simulating the real world that independence is a key factor.
Yeah,
One roll of a die doesn't magically influence the next.
right. It's not like, oh, I roll a 6, now I'm more likely to roll a 1 or something.
Exactly. So when you're thinking about the total possibilities over 3 rolls,
Yeah,
you need to consider that range of outcomes for each individual independent event.
yeah. And the transcript touches on some, like, common misunderstandings, too.
Yeah.
So one incorrect thought process is that you could just take one possible roll, say a 3,
Okay.
and multiply it by 3, as if you somehow rolled the same number all 3 times.
Right. As if it were predetermined.
Yeah, exactly. Another flawed idea is that the die suddenly becomes an 18-sided die,
Right.
or that like a single event could produce a sum between 3 and 18.
Mm-hmm.
It's really the accumulation of those 3 separate random rolls
Right.
that leads to a sum within a certain range.
And I think the crucial insight there is the distinction between a single random event and the combination of multiple random events.
Yeah,
The range of the possible sum will always be wider than the range of a single component event.
gotcha. Okay, let's shift gears slightly and look at an example that involves a little bit of coding structure called a loop.
Okay.
So imagine we have a variable, let's call it I, and it starts off with a value of 2.
Okay.
Then we have this loop that keeps going as long as I is not greater than 4.
Okay.
Inside this loop, another variable pick is assigned a random value between 1 and the current value of I.
Okay.
Again, that's inclusive.
Uh-huh.
The transcript asks us to think about the possible values that pick could take on as this loop runs.
Yeah, this is a clever example because it shows how the parameters of our random function can actually change as a program is running.
Right, like it's not just fixed at the beginning, it can actually...
It makes the possibilities dynamic.
Yeah, exactly.
Yeah.
So let's walk through it the first time through the loop. I was 2.
Okay.
That means pick can only be 1 or 2.
Hi.
So if you saw a sequence of pick values that started with a 3, you'd know something was up.
Yeah, something's wrong.
Yeah, then the loop continues. I becomes 3.
Okay.
Now pick could be 1, 2, or 3. Finally, I becomes 4. And for this last iteration, pick could be 1, 2, 3, or 4.
Right.
So the number 4 becomes a possible outcome.
Uh-huh.
But it wasn't possible at the very first step.
Right. It wasn't initially in the set of possibilities.
Yeah, this really highlights how the set of possible outcomes from a random variable is not always fixed. It can depend on other factors or like the state of the system at a given time.
Exactly. Exactly.
Okay, so let's move into thinking about how we can use this idea of random variables to simulate things that happen in the real world.
Yeah. Yeah.
The transcript starts with a pretty basic one, flipping a coin.
Okay.
A coin has 2 outcomes, heads or tails. How can we represent that using our random function?
Well, since there are 2 equally likely outcomes, a natural way to map this to numbers is to use a range of 2 integers.
Okay.
So you could say we assign a variable, maybe we call it flip,
Huh.
the result of random 1, 2.
Yeah.
Then you could decide if flip comes up as 1 that represents heads, and if it comes up as 2 that represents tails.
Yeah, exactly. It's a pretty direct mapping. But what happens when the chances of different outcomes aren't equal?
Yeah, good question.
Right, so the transcript looks at this spinner that has 8 equally sized sections, but they're colored differently. There are 3 green sections, 2 blue, 1 red, 1 orange, and 1 purple.
Gotcha.
How do we simulate spinning this thing?
So here we need to take into account the different proportions of each color.
Right.
Since there are 8 sections in total, we can still use our random 1-8 function to generate a number that represents landing on one of these sections. The key is then how we assign those numbers to the different colors based on how many sections each color occupies.
Okay, so the example in the transcript shows assigning the numbers 1, 2, and 3 to green
Right.
because there are 3 green sections. Then the numbers 4 and 5 are assigned to blue, replacing the 2 blue sections. Then comes a kind of interesting point.
Yeah.
The number 6 is assigned to either red or orange, since there's one of each.
Right.
And finally, if the random number comes up as 7 or 8, that's assigned to purple, which also just has one section.
Right.
It's interesting how, like, one number can sometimes represent a single specific outcome. And other times, a range of numbers is needed to kind of match the probabilities.
This perfectly illustrates how we can use a random number generator where each individual number in the range has an equal chance of appearing to simulate events that have unequal probabilities in the real world.
Right.
By allocating more numbers in our random range to a particular outcome, we effectively increase the likelihood of that outcome being simulated.
Okay, next up, let's talk about everyone's favorite fortune-telling toy, the Magic 8 Ball.
Magic 8 Ball, yeah.
Let's say we want to program one so that the answer yes appears about 50% of the time.
Okay.
The transcript explores a few different ways you might try to do this using random A, B, and some simple if-then logic.
Right.
And importantly, it points out some pitfalls.
Yeah.
So one approach they mentioned that's incorrect is using random 1, 100, and then checking if the result is exactly 50.
Okay.
Why doesn't that give us a 50% chance?
That's a great question. That gets to the heart of understanding probability.
Yeah.
While 50 is certainly within the range of 1 to 100.
There are 99 other equally likely numbers that could also be generated.
Right.
So the chance of getting exactly 50 in a single random draw from that range is only 1 out of 100 or 1%.
Yeah.
That's definitely not the 50% we're aiming for.
Right. It feels like it should be. But when you actually think about all the possibilities, it's not.
No, it's not.
The transcript then highlights some correct ways to get closer to that 50% probability.
Okay.
So if you're using random 100, one way would be to check if the result is less than or equal to 50.
Okay.
That gives you 50 favorable outcomes out of 100 total, which is indeed 50%.
Right.
Similarly, if you use a smaller range, say random 110, you could check if the result is less than or equal to 5, or alternatively, if it's greater than 5.
Okay.
Both of those scenarios give you 5 possibilities out of 10.
Right.
Again, resulting in that desired 50% chance.
This demonstrates that often there isn't just one single right way to use random numbers to achieve a specific probability.
You can play with the range of the random function and the conditions you set to arrive at the same likelihood.
Yeah, and it's kind of cool to see that, different approaches can get you to the same end result.
Absolutely.
All right, finally, the transcript looks at a spinner that has 6 equal segments, but they're colored with 2 green, 2 blue, and 2 orange segments.
Okay.
The challenge here is to figure out the smallest possible range of random numbers you could use to accurately simulate this spinner.
Yeah.
So your first thought might be that you need a range of 1 to 6 to match the 6 segments.
That's intuitive, yeah.
Right? But if you look closer at the proportions, you'll notice that each color category,
right,
green, blue, and orange, they actually represent the same fraction of the spinner.
Yeah, 2 out of 6 segments for each color.
Right. 2 out of 6 simplifies to 1/3.
Which opens the door to using a smaller range of random numbers.
Exactly. The solution they present is to use random 1, 3.
Okay.
You could then decide if the result is 1 that represents green, if it's 2, that's blue, and if it's 3, that's orange.
Yeah.
And this captures that 1/3 probability for each color using the most compact integer range.
Right.
It shows how understanding the underlying probabilities can lead to more efficient and, dare I say, elegant code.
I love it.
So to bring our deep dive to a close,
Okay.
we've explored how these random variables work as a way to generate possible values in code and simulations.
Yeah.
Remember that key detail?
Yeah.
When you see random A, the range of whole number results you can get from A to B includes both A and B.
Inclusive.
And within any single call to that random function, each of those possible outcomes has an equal chance of occurring.
Right.
And these fundamental concepts are the building blocks for simulating uncertainty and creating all sorts of dynamic and interesting outcomes.
Just digitally.
Brutal world.
And thinking more broadly, understanding these basic principles of randomness is surprisingly important.
Yeah.
It helps us to better interpret the results of computer simulations to critically evaluate algorithms that rely on chance. Yeah.
And even to approach data that involves random sampling with a more informed perspective.
That's such a valuable point, and it leads me to a final thought for everyone out there listening.
Okay.
To chew on, consider how this idea of inclusive ranges and the equal likelihood of outcomes within a single random event might apply not just to the world of computer simulations, but also to how we interpret data and assess probabilities in our everyday lives.
Interesting.
What are some maybe unexpected situations where having a solid grasp of these seemingly simple rules
Right.
could actually lead you to some clearer, maybe even surprising insights?
Yeah.
It's definitely something to ponder, and who knows, maybe it'll spark another deep dive in the future.
I love it.
Thanks for joining us.